So in this lesson, I'm going to keep it to 20 minutes. Right? We're going to talk about the rational function called the reciprocal parent function, which is given by y equals 1 over x. It's called the reciprocal because it's 1 over x. Now, just as a quick review, you don't have to write this part. Okay? We've already covered a few parent functions. One of them is a line where we used a point and a slope to graph it. One parent function is the absolute value, which is a V shape where we use the vertex of HK and plus and minus slope to count. The other parent function we used was x squared, okay? And this one had a vertex, but it also had some symmetry, and it had a very specific set of points that we used to graph. Now, after the parabola, we moved on to polynomials, okay? And for polynomials, we used intercepts and end behavior. Now, the end behavior that we used was based on the degree, okay, and the leading coefficient, and our arrows could be up, up, down, up, down, or down, up. And what we're going to do is we're going to build off of some of this information, and we're going to talk about the reciprocal parent function. Now, in order to do that, we have to identify a few key pieces that we need in order to graph it. Okay, so the first thing we have to identify is the graph. So notice I've outlined it here and I've added my arrows. Okay, notice that it comes in two pieces, so it's not continuous. All right. The center of the graph is at 0, 0. And I'm just going to put a little open circle here because notice that the line doesn't actually go through the center. Now, there are two very easily identifiable points. Okay, so I'm going to do my table of points, much like I would for the parabola. Now, if I plug in 1, I get 1 over 1, which is 1. So 1, 1 is an easily identifiable point. Okay? And then I'm going to plug in negative 1 as well, because I would like to have a point on each of these pieces. Get 1 over negative 1. So negative 1, negative 1. Notice that these two pieces are symmetric. Something else you could note is if I plugged in 2, I would get 1/2. If I plugged in 1/2, I would get 2. So we've got some very similar points here that we could also address. Right? Usually these two are enough, but you can also add a couple other points. So 2, 1/2, 1/2, 2. Notice, right? The pair of points are included. 2, 1/2, 1/2, 2. The negative direction is also included. Negative 2, negative 1/2, negative 1/2, negative 2. So we have reciprocal points. The reciprocal of 2 is 1/2. The reciprocal of 1/2 is 2. Okay, so we've got two more features here. Notice that these pieces are divided up by what looks like lines. This is what we call a vertical asymptote. So I'm using it in a highlighter, okay, because it's not actually part of the graph. It's just helping me divide the pieces. The vertical asymptote, so I'm going to go VA for short, okay, is a vertical line the graph cannot touch. That's because it's part of the domain restriction. Okay, look at our denominator. X can't equal 0. This is our vertical asymptote, and it comes from the denominator can't equal 0. It's those domain restrictions that we have already been finding. Now notice how I said domain restriction. So I'm going to come down here and I'm going to do the domain at this point because I'm looking at the vertical asymptote. I'm just going to follow my graph from left to right. Looks like my arrow goes all the way to the left. That's negative infinity. Pick up my pencil because I cannot touch the vertical line. So this first part is going to be negative infinity to 0. Open because I'm not touching it. Union 0 just on the other side of the asymptote. All the way up to positive infinity. Now, that's the interval notation. An alternative is to say all real numbers, x cannot equal 0 because that's where the domain restriction comes in. Okay, so we've got one vertical line that's helping me divide these two pieces of the graph. We actually have another line that's dividing these pieces of the graph, okay? And I'm going to do this one in a separate color just so that you can see it. This one is a horizontal line, okay? And this one is y equals 0. So now I need to tell you what this one is because it's a horizontal asymptote, and I'm going to say HA for abbreviation. But this one has a different description. This one is describes end behavior. Now you might be a little bit confused because we know that end behavior from polynomials and so far is talking about these arrows, up, up, down, down, up, down, down, up. But because we're going to have a polynomial over a polynomial, right, just like we did in the other examples, we now are going to have the possibility that these things balance each other, okay, and we're going to have these flat arrows, which is actually where this comes in here, okay? So it describes end behavior, which is when x goes to negative infinity, what happens to the y value, and as x goes to positive infinity, what happens to the y value. So this is as x gets very, very large, positive, and very, very large, negative. Now I want to take a look at this expression here, okay? And we're going to work through it. And I'm just going to go in one direction here. Okay, I want to save space. So we have x and we have y equals 1 over x. And if I keep plugging in numbers, okay, I get 1 over 1 is 1. 1 over 2 is 0.5. 1 over 3 is 0.3 repeating. 1 over 4 is 0.25. 1 over 100 is 0.01. 1 over 1,000 is 0.001. But 1 over infinity is very, very small. It's almost 0. So when I look at plugging in very, very large numbers of x, I actually get almost 0. So close, I say 0. Now, if I were to do this in the same negative sense, I would get the exact same answers, but they would be negative. But that's still almost 0. Okay, so the horizontal asymptote describes end behavior. And in this case, it's a horizontal line. That matches this value right here, which is what happened when I actually tried plugging in really, really big positive or really, really big negative numbers to the equation. In that case, now that I've done this horizontal divider, I'm going to do the range. And I'm going to start bottom to top. So it starts at negative infinity. And it actually appears to stop when I hit 0. Okay? So the range is going to go negative infinity to 0. Union, because I have to pick my pencil up. And then I go over here. Just above 0. Notice, not quite 0, but just above it. And it goes up to positive infinity. Similarly, we can write this as all real numbers, but be careful, we're talking about range. We're going to say y can't equal 0. Okay, so now we actually have to figure out how to graph. We've got the center, okay? We have a vertical asymptote and a horizontal asymptote. And we're going to have to do our transformations just like we did here. So I'm going to go ahead and give you your transformation form. Y equals A over x minus h plus k. All right, the center is going to be HK. All right, so this one is going to go right and left. Right? Think about our HK from our other formats. That one's going to go right and left. This one's going to go up and down. Okay? And the A value is going to be our stretch or potentially reflect with those parent points. Right? Our parent points are 1, 1 and negative 1, 1. Okay. Here goes our first example. All right, so we're going to put our sticker in, and I'm actually just going to put it in the middle. I'm going to try to do an example on this side and an example on this side. And I'm going to use different colors so that you can tell the difference between them. Okay. First example, y equals 1 over x minus 5 plus 7. Okay, so I'm going to compare. This tells me that the center, notice that this is going to be opposite, so I'm going to add that word up here. Okay, this is going to be right 5, up 7. Okay, so that's the center, so I'm going to mark the center, right 5, up 7. Now notice in our parent function up here that our asymptotes go through the center. So once I figure out the center, my vertical and my horizontal go through the center. Now the only reason I'm not dotting it all the way through is I want to leave space because I'm going to put a second example on here. Okay, so I've got the center. The vertical asymptote is what comes from the denominator restriction. So that is x equals 5. The end behavior is what happens when we plug in a really, really large value of x. But be careful, because when I plug in a large value of x, this fraction okay, 1 over x minus 5 plus 7. if I think about trying to plug in infinity, I get basically 0 plus 7, which is 7. Okay? The center, also, the asymptote goes through the center. So 7 is that horizontal asymptote. Okay, now I have my 2 points. 1, 1, negative 1, negative 1. All right, 1, 1 from the center, negative 1, negative 1 from the center. And then I'm going to draw those two kind of C curved shapes. Like this. And like this. Okay, and for kicks, we're going to do domain. I'm going to say all real numbers, x can't be 5. And then I'm going to do my range. All real numbers, y can't be 7. Because look at my graph, I'm not touching it. All right, this time we're going to add an a value. Y equals negative 2 x plus 3 minus 4. Okay. The center is at negative 3, negative 4. Opposite, same. 2, 2. Okay, so I'm going to mark my center. The asymptotes go through the center. Okay, so the vertical asymptote comes from the domain restriction, which is negative 3. The horizontal comes from, okay, the asymptote, which is y equals negative 4, which comes from the center of the graph. Okay, and then my points. Okay, so 1, 1, negative 1, negative 1. But because of the stretch of negative 2, right, got my stretch of negative 2. So it's actually going to get taller and it's going to flip. Okay, so I have to times by negative 2. All right, so I'm just going to circle. Okay, so from the center, we're going to count our points. 1, negative 2, negative 1, positive 2. And from those points, we're going to draw those curved shapes. Now notice we've sort of divided this up into 4 sections. This point in the bottom right means I'm going to stay in the bottom right section as I draw my curved shapes. Okay, pause until you're able to get these 2 graphs down. Okay, we're almost at our time mark, so we're going to do one final example here. This is example 2. Oh, domain and range. Domain is, I'll write it in the other format, negative infinity to negative 3 union, negative 3 positive infinity. I'm doing it off the graph. I'm going left to right. And now the range starts at the bottom to top, negative infinity to negative 4 union, negative 4 to positive infinity. Now you can pick your format. You pick whichever one seems more reasonable. This one usually is a little bit quicker to write, but this one also is an acceptable choice. All right, last sticker. First we made the graphs. Now we're going to go backwards. Okay. And I'm going to write down my transformation form. Okay? Because we're going to build off of y equals a x minus h plus k. So I'm going to start looking for these asymptotes. And I'm going to mark the center. And I'm going to start pulling out my information. 3, 2. Now notice you've got a couple other points labeled here. What are the x-intercept and the y-intercept? Okay. Now that I have the center, I know that this is the HK. So I'm going to go ahead and I'm going to plug that in. And in order to find A, just like we did before, you could try to count the points from the center. I'm just going to draw on my asymptotes. Or you can pick a point and solve. So I see this point here, which is 4, 0. I'm going to plug that one in and I'm going to solve for A. Okay, so the y coordinate is 0 and x is 4. Okay, so I'm just going to subtract 2 and we get a is -2. So the equation of this graph, right, pick out the center, find the a value. -2 over x right 3 up 2. Now, next class, please come prepared to do a transformation graph, either writing the equation or creating the graph. Make sure you can do your HK and your A value. We are also going to work on solving for x-intercepts, which is where you plug in y equals 0. And we're going to work on adding y-intercepts to our graph, which is where you plug in x equals 0. Notice that this is just some solving that we've already practiced last unit.